In this segment, I want to look at a different way of representing regular expressions and compare it to what we did in the last segment, where we represented them as functions. So if we model regular expressions as functions, we can build them. We can build them up using the combinators like bar 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 and sequencing. And we can apply them to strings. They're functions. We can take a regular expression, apply it to a string, and that will give us the answer that tells us whether or not that expression matches that string. But we can't do anything else with them. We don't have any notion of what, given a regular expression, it's just a function from strings to booleans. We don't have any idea of what it's like as an expression in itself. There is an alternative, however. What we can do, instead of modeling regular expressions as functions, we can model them as a data type. So here I've defined the data type RE, and you can see there are 5 different cases that correspond to the 5 different ways that we can build a regular expression. There's the value epsilon, there's a constructor ch, which takes a character as its argument, and then there are 3 recursive constructors. There's the OR constructor that takes 2 regular expressions. There's a seek constructor that takes 2 regular expressions again. And there's a star constructor that takes 1. But of course, this representation just gives us data. There's no behavior. It doesn't tell us what these expressions do in the way that our original representation did. So you might argue we've lost something by doing this, but in fact, we haven't. But before we talk about that, let me just show you what our example looks like into this new representation. So previously we built this regular expression by applying the function star and char and so on. What we do here is something very similar. We apply the constructors, and that gives us this value of the type RE. So it's a structure and we can examine that structure and say, what's the outermost constructor? Oh, it's a star, and then we can see inside there's an OR and so on. So it's got a structure we can examine, and in fact we can also recurse over. And perhaps that's the key to the power this has, that we can write a function over the data type RE that interprets each of these as a regular expression. And so we haven't lost anything by going for this different representation. And here indeed you can see I've written this function called match that takes an RE to the corresponding regular expression. And so match of the RE epsilon is just the function epsilon. Match of CHRC is char C. And in the recursive cases, to match OR of expression E and F, we have to match E, match F, and combine them with the 3-bar operator. So what we're doing here is what this function does is it replaces the constructor like OR with the function 3 bars, or seek with the angle plus, and star as a data type with star as a function. So we're able here, given we got the data representation, to do that recursion, and that allows us to define a function that explicitly matches these REs. So we can get all that we had with the functional representation. But we can also do more. Because we've got access to the structure, we can do something like simplifying. And this should remind you of what we talked about when we looked at the EXPRA case study back in week 7. So here I'm writing a simple function that takes an RE and returns a simpler one. So if you sequence epsilon with an expression or an expression with epsilon, it's just the same as the expression itself. If you do star of E, that's the same as doing star of E. And you can think of adding as many particular cases as you want here. And then the bottom case, if none of those matches, you just simplify x to x itself. So you can see there that we're able to simplify and so on. And you can imagine you could define other functions that might tell you when two regular expressions are equal, or when one regular expression matches as many things as another, for example. So using over the data type RE, we can define a whole range of different functions, including the original functional representation. Let's just reinforce what we're doing by dropping into VS Code to see what this looks like. Here we see a similar definition. This time we've defined exp, which is of type RE, to represent our regular expression AB or A star. So what we have now is a data representation of that regular expression, but we can turn it into a function representation using the function match. So if we say match exp empty list, we get exactly the same behavior as we got for the function f. So we're getting here the same similar behavior exactly as we did before. So we can either represent the expression as a function directly, go straight to that. We build it as a function using the combinators angle ++ and star, or we can build a data value representing the expression and then using the match function turn it into a recognition function. And the things that we have here get called by the term shallow and deep embedding. When we represent things directly, all we can do with it, we can build them obviously and combine them, but the only thing we can do is apply them. They're represented as functions, so we can't examine, we have no idea of what their structure is. Whereas if we represent them as data, we can define functions over the structure, including the shallow embedding itself. So we can interpret them, and that allows us to get the shallow embedding, but we can also do things like simplify them. We can do other things. I mean, we could, for example, compile them in a way we compiled expressions into a sort of pattern matching machine and so on. So the deep embedding gives us a more powerful embedding, but it means that instead of directly having the representation as functions, we can get that interpretation only by defining it using a match function. So we get simplicity from the shallow embedding with less functionality, but we can do more with the deep embedding, but we have to work a bit harder in that we take the data item and then we interpret it or simplify it or whatever. We have different functions which get it to behave in different ways, exploit different aspects of it. So this has been a case study that's shown us something about domain-specific languages and embeddings of those languages into Haskell, but it's also been a lesson in how to use functions to represent data objects that we want to model. And I think it's a powerful way of seeing that we can treat functions simply as data in a way that it's not possible to do in other languages.